And it keeps changing too. Anyway, so let's take a look at this one here, analyzing input data. This one here, you get to see what you have to do to prepare data, and this is pretty interesting. So there's something about checking the versions, and here, let me pass that to you. All right, so here, what we're going to do is get some California house price data. So we download this thing, and we'll get a quick description of it here. Let me go to my, okay, let's make a new one again. File, move to trash, return to Colab. New notebook. Good. I got enough bandwidth to do this. This is a handy thing. If the bandwidth is going to be terrible, all I'm doing is passing a few lines of code up to Google and getting a few lines of code back. So even really weak bandwidth should be enough to use Colab. And by the way, tomorrow's workshop will mostly be using local virtual machines. We don't actually need the internet hardly much at all. So anyway, so here we are. There's the data, longitude, latitude, the total number of rooms, population, and the house value here. It's broken California into regions and giving you housing data, and we're trying to make a machine learning model that will predict the data. So you can do head, and here you can see and all these are numbers except for proximity, which is something like nearby, an alphabetical thing in the last column. So you can do categories and counts of the data, telling you how many values there are in that last column. And you'll see there's 5 on an island, and the rest are in things like ocean and near bay. So that gives you information about the kind of data you got, and you can use describe to get statistics with like median and standard deviation and percentiles and stuff. That's how you get an idea, and you have to do this. This is the stuff, if you look at something like there's an election, and the networks are predicting, we only have 10% of the votes, but we can already predict the winner. This is what they're doing, this kind of stuff on the data. It is really black magic. And what's going on here is you have to add human judgment into processing the data, which is then processed by machine learning. It's not at all like the machine does all the work. You have to add all the sense to it. So here, you can make histograms of the data. So this should work. Let me try this one. The fact that I skipped the in-between stuff, I don't think it matters. All right. So this will give me, yeah. So here's the histograms of the data. You can see, for example, it's not a bell curve or anything. It's California. So there's a bunch of stuff near San Francisco and a bunch of stuff near LA and not much in between for longitude and latitude. And you can already see some weird problems. Like here, there's a huge peak at the maximum, which suggests that this data doesn't really measure the house value, but there's up to some limit, and everything above that is just rounded off to this. So that's probably not reflective of reality. So we probably don't really want to train our model on that part of the data. And we're going to make several more judgments like that as we go ahead. So now we can create training and test sets. Now, if you do it randomly, that's what this is going to do. I need another block of code. There it is. Okay, this is going to take the train set and test set. It's going to break it at 0.2. So 80% of it randomly will be the training set, and 20% will be the test set. So there it is. Here's the test training set is 16,000. The test set is 4,000. Here's the start of the test set. And so gives you some idea what it looks like. Now, this is in fact not the right thing to do at all. And the reason is to understand biased sampling. So let's take a look at this one. Here is let's assume that in America, we got 51% of people are female, which apparently is the number. So if we run a random sample of 1,000 people with 51% of them being female and look at the histogram, the most likely thing, of course, is that you'll have 51% of the people female, but you might have a really different number, like 55% or 47% female in your sample. If you do random sampling, you often get biased samples that incorrectly sample something that's important. So if you know that some variable is important, you have to not randomize the sample of that variable, which is kind of nuts, but that's how it works. What you have to do is what's called stratified sampling. So here we can figure that the housing price in an area is probably related to the median income of the area. If you're in a poor neighborhood where people don't make much money, the house price has to be lower. So we probably don't want to randomize sampling median income. So what you do is you break the income into categories, and now you make sure that the percentage of the sample in each of those categories is matching the percentage in the population. So it's not a truly random sample. So that's what this does. This creates appropriate strata and lets you see them. You see, not that they're all equally probable, but these are 5 categories of income. And now you can split the data into not random samples, but stratified samples. So I should be able to do this, although I might have to run the code. I think I have to run the code before it first to create the information. So this will create the strata and chart them. So let me start with that. All right, there we go. Okay, that created the strata and charted them. And this, that's just viewing it, that doesn't matter. Here's splitting the data. Okay. Yep, so it splits it. Now the training set has 35% in this category and 31%, and the test set has, to 3 decimal places, a perfect match. So you didn't make a random sample, you made it exactly right. And this is a more representative sample, not a random sample. And now you can examine the unstratified sets, and you'll see that they don't have this property, that each category is got exactly the right amount. This is the random set. This happened before. Just ignore it and go on if this happens. This is some kind of weird problem which appeared and then it went away and now it's come back. I think it must be Google Colab updating stuff. You know, we're living on shifting sand here. Everything is changing. ChatGPT keeps updating, and each one of these things we're using is changing because we didn't wait 5 years until it settles down before learning it, because we don't have time for that. So, you know, so you'll see some weird problems. Anyway, so you can visualize the data, and here's where you get to put more interesting consequences. So here's the data by latitude and longitude, which just shows the shape of California, but the thing is there's a lot more data here than you think. The dots are covering other dots. So what's better is to use transparent dots. And if you do that, then you can get a clue. There's not very much out here, a lot more there, but what's even better is to include population and price and colorize them, and now you have a lot more data. Population is the blue to red here, and I think somehow the price is in there too. I think the price is like the size of the dots or something. Anyway, you can include a lot more data, and then you can do correlations, and this is where you get something pretty important. These scatter plots are the ones that's going to show me. Let me see if I can run this. I don't know if I have to do all the steps in between or not. Let's see if this works. I want to add another block of code. I'll use this one that failed. Put it in there. All right, it's running. Okay, so what is correlating variables? Median house value and median house value. So that's just a histogram. But notice here's something that clearly matters. This is median income to median house value. That's what we said before. So when the income goes up, the price goes up. Here's something with some trend. And you can notice a lot of interesting things here. You can notice which parameters matter and which ones don't, but you can also see some problems in the data. And here's the one that gives us the most important thing: median income versus median house value in more detail. So let me do that. Another block of code. Okay. Now you can see the first problem I noted before. What is this garbage? A huge pileup of data at $500,000. That doesn't look right. You can see there's 450,000, 350,000, and look at 370,000. There's another block of data which looks out of place. That probably means that some of the number data we had to feed in here was wrong, or rounded off, or put in the wrong category or something. So this is where you do something which I sort of shudder to as a scientist. You remove the data you don't like before fitting the model, but that's what you really do. It's the problem. You know, the fitter is stupid. It will fit all the data, and the human is the only intelligence, and all your data is coming from God knows where, and it has flaws, so you add human judgment here. That's why, you know, when they predict, like, who's going to win the election, then they argue. You did it wrong, you did it wrong. It's not a science. It's not an algorithm. It's more like an art where you're making these weird judgments. Well, you have to ignore that. You have to ignore that for this and that reason. And you have to double this one and weight this one more than that one. And you could argue all those statements. None of them are like really clear whether you're doing the right thing or not. It's like experiments. So then here's another one that's mind-boggling. You can make new columns combining attributes because there are attribute combinations that matter more than the attributes by themselves. The individual attributes are not correlated much with the price, but here's one: rooms per house and bedroom ratio, bedrooms to total rooms. Those things, as you might imagine from real estate, they rate a house. A 4-bedroom house is different than a 2-bedroom house. And so here's some new combinations which have more correlation with what you care about than any of the input data does by itself. So that's another kind of mind-bending thing. Now you look at these correlations. House value is what we want, so that's 100% correlated. Median income is 68% correlated. The rest of them are in a small change, but notice I have 15% is all I have here, but if I make the bedroom ratio, it's 25% correlated. So combining two of these numbers that are not much correlated creates a new synthetic thing that is highly correlated. So I would be better to use that as the thing to learn on than using the raw data. So, this just gets you started with the joy of this stuff. And I should mention, I had a lot of this I got from one of these textbooks. These 2 textbooks I put here, they are very good. They show the dirty stuff you have to do to take real data and massage it until it's ready and adjust your model. And it's not automated at all. It includes a lot of human judgment, what you train on, how long you train, which training technique you use, and all that jazz. There's a lot of adjustments here. So let me just mention a couple others here about these technical inner components. Classification here, we're going to get some data, and this is the MNIST data. We're going to use this a lot. This MNIST data, I don't need, I can hold down. This MNIST data is a bunch of numbers that were entered by American census takers. 70,000 digits written down by humans in censuses, and so these are numbers, and you want to learn to take these different written forms of numbers and reduce them to digits. So there's a database of 70,000 of these with the right answer available. And you want to train a model to do this. So here, we're going to take 60,000 of them and call it the training set, and the rest, the other 15,000 or something is going to be the test set. And now we're going to simplify it. We're going to just go down to whether it's 5 or not 5. We're not going to sort it into Ken categories. We're going to sort it into 2 categories, 5 and everything else. And that's what this does. And then we can make a linear model where you have the input pixels go into a bunch of neurons that have all the data from all the pixels, and then they feed into one neuron. So we're going to have one neuron do it. This is a linear model where all we're going to have is a linear combination of the data from every pixel. So we can train a classifier, and you can measure its accuracy. And here's the accuracy, I think down here, we did it 3 times, 95%, 96%, 96%. So even just a simple linear combination is enough to tell a 5 from a non-5. Now you can also rate it by confusion matrices, and this shows you all the numbers you need. This is how many correct non-5s and correct 5s, and this is the incorrect ones that should have been 5s, but you called them non-5s, and this is the other one, or else it's the other way. These are the 4 possible categories, the sort of truth table. Then you can define something called precision, which is true positives over true positives plus false positives. That's one way to get a number. There's something called recall, which is true positives over true positives plus false negatives. And there's something called the F1 score, which is precision times recall over precision plus recall. These are these statistics that people use to rate your model. And they each define different sorts of things. So now, remember we combined all the information from all the pixels into a single neuron that has a signal coming out of it. And you take that signal and you can choose the threshold. If you choose a low threshold, then it will have a high false positive rate. And that gives you precision less than recall. The sweet spot here is where precision equals recall. You can have a high precision, so it never fires unless it's sure it's a 5, but you accept missing more of the 5s, so you have more false negatives. And this is just like, I remember teaching this in all my CISSP classes, this is what you have for like biometric identifiers. Do you want the biometric identifier to have a low threshold, which means it's easy for the customer to use, but it's more likely that a bad person can get in? Or do you want a high threshold, which means the bad guys are rejected, but the customers are rejected frequently because it's really picky? And you might want either of those. Anyway, you can view the raw output of the neuron here, and you can change the threshold values and watch it change the performance of it, and graph the precision and recall as you move the threshold around. And this is another internal detail, which things like ChatGPT have glossed over this. But if you want to make your own, which I highly recommend, and I think that's what everybody's going to want on the job, they're going to want, why don't you make our own machine learning to do this and that? This is part of the dirty nitty gritty you got to go into. as you make your own. And there was one more in this category, which is data poisoning, which is poisoning the input data to teach your model to do things wrong. So here we get 1,000 images, a handwritten digit, 0 through 9. I think, yes, the MNIST data again. So we get a bunch of this data, and now we view the predictions of the model, where I'm going to get the correct and incorrect predictions. And you see it's mostly correct. It's getting about 10% of them incorrect. So then I summarize the sets, and now I'm going to poison 10 of the ones. I'm going to trick the model into identifying more ones as twos. So I create a poisoned data set here. And what I did was just change the labels. I took a bunch of twos and changed the labels to 1. So it's learning on data that is incorrectly labeled. And then I add those in and train it. And you'll see when you train it from the poisoned set, the poisoned model gets 2 ones incorrect and 11 twos incorrect. The poison had very little effect. And there's a level of poisoning if you poison 30 of the ones by telling him they're really twos. There is a point, of course, when it starts learning wrong. And that's one simple example of poisoning. You can practice that one. That's one of the attacks. So that's all I wanted to say about that section. Let me stop this video.